Yeah, so we have, again, all the math skills. We're done with, well, we're constantly doing problems, but there's really not any, standard catalog of math tools you need outside of just taking derivatives and applying these things. So make sure you understand chapter 1. That's the bread and butter for this course, okay? So we'll reveal all sorts of properties of electromagnetic fields. It's governed by literally divergence theorem and Stokes theorem, and even Helmholtz theorem, okay? So regardless of whether you went through the details of Helmholtz theorem from the video, the statement itself is very simple, so you'll see its meaning constantly. So again, I'm trying to use these properties to illuminate the geometric features of this theory. You've heard these terms before in physics too, Gauss's theorem, so we're headed towards proving Gauss's theorem, okay? So, suppose you have a single point charge, and I'm going to be nice enough for now, for once, and place this charge at the origin. It's a charge Q. Then the electric field at any point, okay, is given by, what's that? I remember this way as well, KQ over R squared, R hat. We have shown, if you straight take the divergence of this, you'll get 0, right? But what we have shown is slightly better than that. Well, it's 0 everywhere except, but when R goes to 0. So there's a delta function in there. So then, divergence of E equals, let me bring out KQ, which is a constant, divergence of R hat over R squared. Remember, this K is 1 over 4 pi epsilon naught. Okay? And remind me, this is, so KQ, this is 4 pi, yeah? Just at the origin, there's a delta function. So I can even write this as Q over the 4 pi's would cancel, epsilon naught delta Q over R. Fine. Now what I'm going to do is for a fixed R, I'm going to take E dot dA. And I think my freehand circle is better. And despite how it looks, this is a circle of radius r. So on this sphere, I'm going to compute E dot dA. It's a closed sphere, sphere of radius. This is the domain, sphere of radius r. Okay, it's a simple integral, so I would get this to be equal to, well, let me put the integral limits first. KQ over R squared, R hat. Now dA is also in the R hat direction, so that works out very nicely. R hat. Now on a sphere, what's the radius? It is R squared, but oh, so again, this is also R squared. R squared no dr sine theta d theta d phi. So let me write this as 1 over, because 4 pi always cancels. Q, look at this and this cancel. And then we know what sine theta d theta d phi is. D phi is 2 pi, sine theta d theta is 2. So it's 4 pi. And that's exactly the reason we defined epsilon naught and k in this fashion. And what you get is Q over epsilon naught.
The integral for was 0 to pi and 0 to 2 pi, right?
0 to pi for theta, correct. 0 to pi for theta.
Yeah.
And 0 to 2 pi. Yeah? Did everything cancel off? Like it should?
Are we given those of the other R hat and the other
R hat dot R hat is 1.
Yeah.
This R hat came from E.
Uh-huh.
This R hat came from the area element.
Okay, yeah.
Yeah. So that goes away. We're integrating only on the surface of the sphere. So all R is just capital R. There's no free variable. See, normally the dA would be R hat, R squared sine theta, d theta, d phi. But again, for us, R hat is just uppercase R. Yeah, James? Good. All right, well, that's a simple enough area, a nice enough integral. Everything just worked out, and we in fact get a constant. But I would like to now know what happens, well, maybe I can assign this as homework, huh? If we integrate over the surface. Obviously, you know that we're not going to integrate over that surface. There's a trick. So let me do it. Let me give things names. So let me call this S2, and let me call this surface S1, okay? What I'm going to do is divergence theorem in this volume. The volume is between these two surfaces. So this is a perfect sphere. Remember, it's a two-dimensional drawing, but it's supposed to be a three-dimensional surface. So there's an inside ball, a nice spherical ball, where we know how to integrate. And outside is a complicated, smooth surface. And the question is, what is the flux outside this surface? The answer, you know, is going to be exactly equal to flux from the inside surface, but I need to show it to you. So we don't have to worry about complicated ways of doing it. So we start with the divergence theorem. The divergence theorem says divergence of E d tau is equal to E dot dA. But in this region, what is the divergence? This is the divergence. Yeah, the divergence is only non-zero at the origin. So this is 0. So I'd get 0 equal to, I have to worry about, in this case, two surfaces, because that volume has two boundaries. So it's S2 plus. Yeah? And for both of them, I have to use outward normal. So in this case, the outward normal that I'm going to use is going to be the following. Well, not in this case. It is the outward normal. And it's S2, so I'm going to call this N2. Right? Normal vector of the second surface. What is this? Correct? So then I get E dot dA S2. This we have done. It's that, but when we did this, what was the normal we picked? Positive R hat. But what do we need now? Or, what is it that I've shown? Yeah. No need to do any complicated integral.
So how do you get back to that second one right there?
From here to here? Yeah, so this is the volume integral, this is the boundary. This volume between these lines or between the surfaces has two boundaries, the outer boundary and the inner boundary. You have to integrate through all the boundaries as you have discovered in your exam. Yeah.
And that negative just comes from the inner boundary with it.
Yeah, so the previous answer we got was using the outward normal. But in this problem, we don't need the outward normal, we need the inward normal. So it's, every time the dA vector is being replaced with the negative of it, so the negative just comes out. So from here, we can construct the integral version of Gauss's theorem.
So this would be the boundary of S1, like
This one? It is, but with the outward normal, right? So this is using minus, I don't know where to put the notation. Oh, no, I guess I should put this over here. This has minus R hat. When we just did the example that I erased, I had plus R hat. The minus just simply comes out. Yeah? So I think this is correct Gauss's. I don't know how many S we need to
I don't
put.
think you put that third S.
You don't?
If you
I've seen-
end with the S, you just put the.
Okay. I will default
The same
to.
with the Stokes theorem.
Yeah,
Stokes
yeah.
is, but you don't do
Yeah.
the extra S.
Yeah. You would think I'd remember these simple rules, but
I,
but I won't dispute it. Yep. So suppose.
we used to do that, and it looked so weird, it prompted me, I actually looked it up. Like,
Yeah.
why is it so? So that's what I found out.
Yeah. Even if it is one S, I think you don't put.
Yeah, if it ends with like a S sound, you wouldn't
Yeah.
say
Yeah.
just one,
Yeah.
and then you just get rid of that.
Yeah. So now suppose you have Q1, Q2, Qn, and I ask you, what's the flux through that? Well, because for this one, doesn't matter if it's a nice circle or a, outside an envelope. No, it doesn't. So it's Q1 over epsilon naught plus Qn over epsilon naught. I want to clarify one more point. It's not quite what I want to say. What happens if you have charges? These are all charges. And I ask you to find the flux. I want to say this is the total charge, right? But you can see enclosed. Only if it is inside will it count. If it is outside, it won't count. You know why? Look, for every line that penetrates, if you're looking at this charge, for every inward flux, there is a outward flux. This is the integral version of Gauss's law. And we want to do more than the integral version. We need the differential version as well. So I can write it as dA equals 1 over epsilon naught. Total charge enclosed. I may have to use delta functions if there are point charges, right? Or if there's surface currents or whatnot. But we know how to use them. But I can write total charge as rho d tau. Correct? But I can use divergence theorem for this and say this is equal to what? Well, divergence of E d tau for any volume. I can do slightly better. When is this true? Not for just one fixed shape, but this is true for any volume. Can that happen? An integral of a function that is 0, given if you integrate it over any volume. Let's not overcomplicate it. Let's think of a function of one dimension. If the integral of a function is 0, over a certain length, can you say the function is 0? Certainly not. Because I can think of upward area cancels the downward area, negative area, it'll give you 0. But the function is not 0. But that's not what this is saying. It is saying for any volume. So that means area under the curve for anything we choose must be 0. We can choose little bit at a time. Pick a point where this is not 0 and then integrate over that volume, around that volume. But you still get 0. That cannot be. So if this is true for every volume, we will have, and I want you to reflect over this more and more, maybe even check with your real analysis teacher. The only way that is possible is, yep. It has to be 0. The integrand has to be 0. So this implies that. But it's very crucial. Is that a question?
Yeah.
Yep.
What is that piece then? Origin?
This one? Rho, charge density. I replaced the Q, total charge, to be nothing more than integral of the charge density. This is the differential form of Gauss's theorem. Gauss's theorem is very handy when you have certain symmetries. In fact, if you want to find the gravitational potential energy inside the Earth so that we can build our tunnel, we can use the gravity. Assuming the Earth is spherical and homogeneous, yeah? Then we can use Gauss's theorem. Homogeneous at least in radius. At every radius, the Earth looks about the same. Yeah? And the weird thing about physical laws is all these equations are, you can violate it slightly and the result only violates slightly. So if you're not worried about too much accuracy, and we're not. If, for example, if I ask you how far is Montgomery, you're not going to tell me 42 miles and 7 inches. Yeah? So it's amazing how it works out. So if you change the data continuously, the fields also change continuously. So if your error is not that much, imagine if that was not the case, you wouldn't discover any laws unless you had the perfect one and perfect instrumentation. So this is the differential version of that. They're both Gauss's law. They tell you the divergence of an electric field. From Helmholtz theorem, what are the two things you need to uniquely describe a vector field? The divergence curve. So if you need a law to describe the electric field uniquely, I have to prescribe its divergence and its curl. So we're one half of the story done for electric fields. In day one, I should have mentioned something that I thought you would know because I was quick to jump into a problem because you've taken physics too. This is electrostatics. Charges are not moving. It'll take a whole semester to flick a charge. So we'll do electrostatics, we'll do magnetostatics. We just put things in place. We won't turn a current on for a whole semester.
And that comes to the second part?
That's the second. That's electrodynamics.
I'm gonna drop the class,
I knew.
Right. You can't even do V equals IR. That's very complicated. That's so many things going on. Okay. All right, so let's do some problems. When can this be useful? So we want to know what the gravitational field is inside the Earth. But this is a course in electricity and magnetism, so we'll take a sphere and fill it uniformly with a charge. It's a worked out problem in the book, but you've seen this from physics too. Hopefully you recall, as I mentioned, that these are the kinds of problems that you have done. Since it's an example from the book, let me at least state which one it is. Example 2.3. So find the field outside a uniformly charged solid sphere of radius r and total charge q. We're going to do it inside as well. So this is example 2.3. The biggest bane of my teaching career is having to draw pretty diagrams. So we have a solid sphere of radius r. Okay, and a total charge of q is put in the sphere, and it's uniformly distributed. What does that mean? That means the charge density is total charge divided by volume, which is
What was it?
4/3 pi r cubed.
Oh, that's the other, pi r squared. Right?
Yep. I think it seems like we have done this problem before. We did it for a shell. What do you think the field outside is going to be? It's like a point charge. Yeah, but that's not the point. No pun intended. We're doing Gauss's theorem. So I'll divide this problem into two. For r greater than r, which means outside the sphere. What I'm going to do is draw another partial circle for my lack of ability for drawing a bigger circle. And this is the circle I'm going to, some circle of radius r greater than r. Already, this is what I mean by symmetry. Already, there are several things you know about the electric field before you do the problem. It's very important for you to realize what symmetry means in mathematics and physics. Will the magnitude of the electric field differ from this point or this point? No. Which way can the electric field point? Or inward. Yeah, it's a positive charge, so we know it points outward. We just did Q over epsilon naught is the flux, so it's pointing outward. Fine. But the point is, E of R is nothing more than some E, which is only a function of R, and it points in the R hat direction. So then we have E dot dA equals Q enclosed over epsilon naught for Gauss's law. Whenever you use Gauss's law, I told you can only do it when there's high symmetry. The integral reduces to multiplication. If you're integrating, you're not using Gauss's law. Watch. E sub r hat dot r hat r squared sine theta d theta d phi. R hat dot r hat is 1. This is a function of r. Are we integrating over r? No. Where did 4 pi come from? Sine theta, d theta, d phi. How much charge is inside? Well, all of it. You are not integrating. Let me be very clear. Therefore, guess what? Or, where we started out from, this is k, q over r squared, r hat. Well, we knew that all along. But now the point is, we can do the other case. Yeah? You may have to do careful algebra. I'll show you what that means, but never an integration. R less than R. In this case, where's my sphere? Yeah, it's over here. And this is what you have to worry about. What's more dangerous in science, in physics, more than equations, are words. They're tricky. We don't pay attention to that. Well, first of all, very good? Nothing changes. But what's the Q enclosed? Not big Q. Function of? Exactly. So let me do this. It is going to be rho times this volume. Thankfully, I have rho over here. Q over 4/3 pi r cubed times 4/3 pi r cubed. Or what do we have? Q over 4/3 pi goes away. QR over Q over epsilon naught r cubed over r cubed. Yeah? Look. Q over epsilon naught. Now I'm going to set it equal to that. You guys are good with math, so tell me what you get. Electric field as a function of R is, there's a 4 pi epsilon naught, so I get Q over 4 pi epsilon naught. And then what do I get? Yeah? So this is E out, oh sorry, E in, inside, E out, which is Q over 4 pi epsilon naught, 1 over R squared. Note that both of these guys agree when little r equals big R. This becomes 1 over R squared, this is 1 over R squared. So if I were to graph this, the value here is KQ over R squared. Outside, it is, we get used to this, huh? Dropping off as 1 over R squared. On the inside, correct?
Can you, the first line you drew, for KQ over R?
Yeah, I mean, there's no line here. It is just the value KQ over R. In and out agrees at little r equals big R, and that value is KQ over, sorry, R squared. Yeah? Outside, the electric field falls off. Inside, it is increasing linearly. What increases linearly? Magnitude. Simple harmonic motion. Yeah? So if I do the gravitational version, in the gravitational version that, well, if you want, you might recall it even this way. In the case of gravitation, there's a minus g m1 m2 over r squared, so it becomes minus m over, I don't know, some g, whatever it is, with r. It's minus r. So that's what I was referring to. If you have a solid mass and you drill a hole and you jump into the hole, you're going to simple harmonic oscillate. Gauss's law tells you this. So you can drop luggage and somebody in a fishing boat in the Indian Ocean can just pick it up. Might have to reach a little because of maybe.
But wouldn't the product go into
So you can see these are very powerful, very elegant. We're able to solve tougher problems, but it's the same bag of tools we'll just need over and over again. So the difficulty now in E&M is only conceptual understanding. It's not going to be math-based. That also means